Okay.
Live.
All right, let's get started then. This is the third lecture for RAP. We're going to be talking about mixers, what they are, why we need them in a bit more detail. We've kind of talked about it in the past few lectures as well. Before going into the topology we'll be using for mixers in RAP this year, some quick analysis on how it works, why it works, stuff like that, and yeah, that's basically it. Before we get into that, a few announcements. One, teams were announced a day or 2 days ago now, I think.
Yeah, I think
on Monday night, Tuesday morning-ish. So please make sure you reach out to your teammates, get a conversation started with them around assignment 2. Generally discuss how you want to proceed for the year, what your different strengths are, stuff like that. Second thing, we are having a work session this Saturday. We figured out the timings. It will start at around 9:30 and we'll be there till about 1:30ish. So
I'll be there for the first half of it.
yeah, Tyler's driving home later in the day, so he'll be there for the first half of it. I'll stick around till about 1:30. So we'll be there in the lab for those 4 hours on Saturday. Help with assignment 2 if you need any help, or if you just want to work on it with other people in the lab. Assignment 2 in turn is due Saturday at midnight, so please make sure you get checked off by then. And while Sahil, we're in here, and while we're doing the lecture today, we will not be releasing the assignment for assignment 3 tonight. I know that some teams have gotten pretty far into assignment 2, and so you might be sort of ready to get moving on assignment 3. But just to make sure that everyone in the project is on roughly the same page, we'll be putting assignment 3 up probably sometime during the Saturday work hours, but basically you can start working on that from Saturday onwards as well. It's a slightly shorter assignment as well, so we don't think it should be too big of a problem. Finally, we were just briefly discussing something about the social off camera as well, so for the benefit of those people who are watching this later. We're thinking we might hold the hype that we voted on sometime next quarter. We might do a dinner type thing sometime in the next week. Check Discord, keep an eye on it, and we'll plan it out through there. I think it'll be fun. You get more of my bad jokes and more of Tyler doing my bad jokes. All right, I think that's everything on the logistics side of things. Main thing for everyone to keep track of is just work session this Saturday. Come by, it'll be a good time. All right, so mixers. Let's get started. So first of all, what are mixers? Really simply, a good mixer is one that takes in signals at 2 frequencies and multiplies them together and gives you an output of those multiplied frequencies. There's a whole bunch of other properties that get brought up when you're designing a physical mixer in terms of where you're inserting the different signals from and what kind of properties it has with regard to those frequencies, but we'll get into that a bit later in this lecture. But at a high level, at a systems level, right, when you're drawing a mixer in your general block diagram for your, so this is your, say, source, right, then you put that into your amplifier, right, and then that goes in one place. Then you have your local oscillator, and out comes this, and let's say it goes into your, I'm not quite sure what that,
Filter and then
yeah, so filter, and I'm not sure what the thing for an antenna is, so I'm just going to write antenna. So this is like, when you're looking at it from a rough like systems perspective, you generate your signal, amplify it a bit, mix it with your mixer, with your local oscillator, which is your carrier like we discussed last lecture. You filter it to get rid of the other frequencies that are generated, and I'll get to that in a second, and then you transmit that through your antenna. So that's what the mixer does. It takes 2 frequencies, multiplies them. The question then is, why do we need this? There's actually a couple of different reasons, right? One real, just off the bat, the logistics of actually transmitting, right? If you recall from, I think, 101A, 101B, something like that, or just generally from a physics course you may have taken, or if you're learning this for the first time, for transmission quality to be good, you want the length of your antenna to be greater than equal to lambda by 4. Lambda being the wavelength of the signal you're transmitting or you're the main wave that you're transmitting, right? Not the thing you're modulating onto it, but the main signal you're transmitting. Now, if you take, for example, an audio signal that maxes out at like 20 kilohertz, I think that's the human ear range. It's like 200 hertz to something like that.
20 kilohertz, yeah.
Yeah, 20 kilohertz, let's say. So speed of light, lambda is equal to 3 into 10 to the 8 over 2 into 10 to the 4. This is 1.5 into 10 to the 4 meters. Even if you divide that by 4, that's like 4 into 10 to the 3 meters. I can guarantee to you that this does not have a 4-kilometer antenna in it, right? So a big reason why we do modulation up to higher frequencies is to make transmission even physically possible, right? To make sure we can use antennas small enough to actually be feasible to use in everyday life and actually work with. So that's one big reason why we need to do modulation. The second thing about modulation though, and this is something that someone like the FCC is concerned with a lot, and that's why we choose 27 megahertz, because they've demarcated it as one of the frequencies that we are allowed to transmit at. I think the next one after that is 433 megahertz. After that, it's like 1.4 gigahertz or 4.1 gigahertz. I'm not entirely sure. So there's a few frequency bands where like hobbyists are allowed to transmit, and they kind of let that be a free zone, if you will. But if you think on the radio, for example, right, as you change through channels, you realize that you're hearing something audible from all of them. So in fact, sometimes the same song on multiple channels. So you have the same frequencies on multiple channels, and yet you're only hearing it when you change the channels. Why does that happen? So again, if you come to the frequency domain, right, and so this is near your 0, and this is where, let's say, up to here is where the human ear can actually hear it. So you have some song, right? Let's say it's Yellow Sweater by Taylor, what is it? Cardigan by Taylor Swift? All right, it's that one by Taylor Swift, right? And then the FCC has defined these bands that the different radio operators are allowed to transmit at. So you then have different center frequencies. And so this is radio station 1, this is radio station 2, this is radio station 3. And they can all use different frequencies as their local oscillator. And despite having the same source that's getting amplified into their mixer, when they filter it and put it into their antenna, what's actually getting transmitted out is something that then is in these 3 different buckets. And you know, there's stuff that goes into how far apart do these need to be based on how wide this is and other things like that. And that's where you get a lot of FCC regulation about bandwidths and other such things. But the key takeaway is this is something called frequency multiplexing, and basically the idea is it lets you have different carriers, different operators, all operating in similar ranges of frequency, all carrying completely different signals, without all those signals getting mixed up and without you basically getting garbage at the output. Your cell phone towers do another rough version of basically this to let thousands of cell phone conversations happen in parallel without those signals all getting mashed up, interfering with each other and giving you meaningless mess, right? But easier to understand example would be something like a radio, where you can then basically scroll through, tune through these and choose them. Fun fact about radios, actually, if you ever open up like a really old radio, the ones that with the physical dials to tune, when you turn the dial, it's actually a capacitor in there, and you're actually moving the capacitor plates closer and farther apart. And what that changes is the resonance frequency of the receiving antenna. And so you're basically changing which band you're listening to by changing the resonance, by changing what frequency your receiving radio is, you know, resonating at. But
I think it's changing the LO, and then you multiply that with whatever.
So this is the receiver end.
Yeah, the receiver end, or like the receiver
Yeah.
mixes in with some oscillator.
Yeah. It changes the LO, and right he is. So that's what we use mixers for. That's what they are. Any questions about that part of it? No? Sweet. All right. So at a system level, that's what mixers are, and that's why we use them. Now we can start talking about the mixer we use and the circuit behind that and why it works.
Yeah, so we're going to be using something called a diode ring mixer. There's a lot of different mixer topologies that you can find online. They all have their own properties and whatnot, but let's see, it's gonna take me a quick minute
Sure.
to draw this thing, so tell them a joke.
Okay, so Tyler was talking about different mixers having different
Tell them
properties and topologies.
Tell them about what happens when you multiply two cosines. That's a good one. That's a really funny one.
Sure. Yeah, if anyone's interested in some of the math behind those drawings I was doing, you can think of it like this. Right, and if you think of this in frequency domain, this is omega 1, omega 2, omega 1 minus omega 2, omega 1 plus omega 2. And again, multiplication in time domain, convolution in frequency domain, flip and drag, you get something like this. So that's basically the math behind, hey, this is how it gets shifted up to those different carrier frequencies, if you're interested in writing it. Then you do the Fourier stuff about decomposing Taylor Swift songs into a bunch of different cosines, and you translate them all up, and there you have it.
Thank you, Viola.
What was the joke? Wasn't a joke?
Let's see. What did the cosine say to the negative frequency?
What?
Don't be so negative. You should have a positive outlook on life. Because you know cosine of negative omega is just cosine of omega, so it's anyways.
I don't know what you were expecting.
I don't have expectations.
Like, I don't know what you expect when you ask me to come up with a cosine joke on the spot, man.
It can be a sine joke too if you want.
This was a sine joke. It flipped the sign.
Alright, enough of that. So here's a diode ring mixer. We're going to break down how it works. So the end goal should be, we have some LO here, in our case, like a last assignment or due Saturday night. You'll have produced two Colpitts oscillators that produce a sinusoid signal, amplitude pretty large, about 1 volt. So that comes in and it should get mixed with what we're going to call our RF signal. So this will be like some information, it's a carrier signal. No, it's subjective. Okay. I'm down converting.
Okay,
Come on. Okay, and then and then here we'll see the mixed versions of these two signals multiplied together. So how does this circuit accomplish that? So we're gonna kind of step through it. So the first thing we're gonna look at is we're just gonna break down this transformer over here. So let me redraw it real quick. Okay, so you would, so we're going to use these transformers. So I'm going to call this okay, so what's going to happen is we have our signal coming in here. Let's say it's something like that, okay? So what we're going to end up seeing is that at port 2, we're going to have, we're gonna basically see that replicated. But at port 3, we're going to see that inverted. Okay, now at first it might be like, how come? So an easy way to kind of visualize what's happening is you can draw kind of three 3 inductors, and then draw the phase dots accordingly. So you see how they're grounded in the middle. So this is, let's call it L3, L2, L1. So this is L3, L2, L1. Phase dot. This is running out. Line 1. Okay. And beginnings. Switch to blue now. Okay. So you can see how because the dots are on the same side, but there's ground in the middle, can kind of be thought of as this. So whatever voltage appears at this node on L1 will be replicated on L2 because the phase dot is there.
Upwards, because the voltage is being replicated, what does that mean about the turn ratio?
Right. Yeah, so what we're going to see is that when we actually wind our transformers, and we'll talk about this later when we're actually making them, but we'll construct them such that L1, L2, and L3 all have the same inductance or same turn ratios. But then since L3 has the dot on the side next to ground, you can kind of think about it as if it were flipped. So that's why L3, that's why the signal here is going to be an inverted version of what you see at the LO port. Okay, so we have that. So let's say so when we're telling you guys to build your oscillators, we said make the output amplitude 1 volt. And if you assume that if you assume that LO is a pretty high frequency, and it's going between 1 volt and -1 volt, then if it's going fast enough, then it's going to be really sharp, kind of like this, right? So this is more or less a square wave. It's technically a sine wave, but since the amplitude is so large relative to the period, you can approximate it like a square wave. So we're going to treat it as such. So it kind of has 2 states of being. So state 1 is this is going to be +1 volts, and then up here, like we said, we're going to see it replicated. So this will be +1 volts. Down here, because it gets inverted, will be -1 volt down here. So the effect of this is it's going to forward bias D1 and D2, and D3 and D4 are going to be reverse biased. Just a quick note, an assumption we make throughout this process is that RF, or our information signal, that the amplitude is much smaller than 1 volt. And we kind of saw that, like in assignment 1, even after being amplified, we used like a 1 millivolt amplitude signal, and then if you're receiving something from an antenna, it'll be comparable in magnitude. Small amplitude. All that is to say that whatever happens here, whatever voltage wiggles here, won't really change the biasing of these. It's completely dominated by what happens at the LO port. Does that make sense? Yep.
Which is why that magnitude of LO is actually important, and when you're designing it for assignment 2, you have to make sure to get it that high.
Okay, so if we say that when that's positive, then D1 and D2 are on, they're conducting, but D3 and D4 are off. So I'm just going to go ahead and erase the reverse bias portions of the circuit. And now we're left with this. Okay. So another observation to make is that so I'm going to just say right now that the voltage at that node in between the 2 diodes, assuming the 2 diodes are equal, is going to be equal to 0 volts. And to kind of see why that is true, let's see, I'm just gonna add a drawing from that side. Let's try one more time. Okay, so it's -1 volt up here, 1 volt up there. So just by Kirchhoff's current law, we know that the current through both diodes has to be the same if there is any current through it. And then using the exponential model for both diodes, let's say, let's call this D1, D2. So you can kind of see how VD1 equals VT ln current through ID1, which is the same as ID2, over IS, which is going to be the same as a through diode 2, assuming that IS is the same for both, equals 2. A long-winded way to say that the voltage drop across both of these has to be equal, since they're both dissipating 2 volts in total. 1 volt minus 1 volt is 0, minus 1 volt plus 1 volt. It's 0 right here, okay? So this is kind of like a virtual ground, so to speak, right here. And the effect of that is, so you can just say that, okay, this circuit, there's a ground right there. So what we're left with is, so we have RF here, dot there. Because we've grounded the other end of that inductor, and here we have IF. So essentially, what we're just going to get, since the dots are on the same side, we're going to get that IF is just going to be equal to RF when LO is in its positive swing. Okay, so far we have when LO is +1, RF is equal to IF. Now the exact same thing happens, but with the opposite polarity when LO switches. So now instead of being in this part of the cycle, now let's say now it's -1. So -1 here. So it switches. This becomes -1 volts. This has opposite polarity, so +1 volts. Okay, so now the other set of diodes is going to be forward bias. I draw it the wrong way. Yes. So I think that, so that touches there, this point. Okay, so the same thing happens.
That goes to the other half of the
Yes,
transformer.
thank you. Okay. This was originally connected to the other side, which doesn't exist anymore. Okay, so this, okay, other inductor. And, okay, so since this node had two diodes that were both reverse biased, so the middle is just kind of floating there unconnected, which means no current, there's no loop for current to flow through this bottom inductor. So it goes away. Then we're left with this. So the end result, this ends up 0 volts again, like before. The only change here is now instead of flowing through this inductor, it flows through this one. Kind of like we saw over there, what's happening here. The phase dot is going to be the other side of the transformer now, which means IF is equal to minus RF. Okay. Is there any confusions about this process so far? Okay. So kind of to summarize, our input LO frequency, its amplitude's really large, so we're essentially using it to switch which set of the two diodes is active. So during one cycle, so when it's positive, these two diodes are active, and when it's negative, these two are active. then depending on which set of diodes is conductive versus reverse bias, it changes which of these two inductors the current is going to flow through. So IF can either be the replicated version of RF or can be the inverted version of RF. And then since we said that the, let's see, yeah, again, and like Vaibhav mentioned, the windings are going to be same ratio.
What's IF and RF again?
They're kind of semi-arbitrary names here. In our case, just say, okay,
RF is the radio frequency, IF is the intermediate frequency.
yeah,
So
just say IF is our output.
So when you're up converting, so in this case, when Tyler is down converting, what he's doing is he's taking a high frequency signal at RF and then multiplying it with the local oscillator LO, and then he's interested in the low frequency output IF.
I see.
So depending on basically whether you're up converting or down converting, which one of IF and RF is your input versus your output will change. So depending on whether you're working on the transmitter or receiver, that would change. When you're transmitting, your outputs are at the RF. When you're receiving, your outputs are at the IF.
Makes sense.
Okay, yeah. So, what's up?
Right, so your LO is your input, right?
The LO is going to be the carrier frequency that we're
No, I'm
gonna
just having trouble, like, how can RF be your input? Just slow that. Like, what kind of signal do you have injecting, what kind of signal are you injecting into RF then?
Okay. For example, later we're going to have a microcontroller, right? And it's going to, using its digital to analog converter, will output a 1 megahertz just information signal that we've kind of encoded a bit stream onto. So we're going to take that 1 megahertz modulated sinusoid, and then we're going to put that into a mixer and mix it with some carrier frequency. So for example, if you're doing it all in one step, you could have a, I don't know, our microcontroller goes through a buffer or something, I don't know, and then be connected to our RF port. What's
the
up?
microcontroller will go to intermediate frequency RF port.
Yes. So just say our microcontroller is down there, and then over here we have our the oscillator that we designed in the previous assignment. I'll just draw it like that for now. So that's connected there. So then what we'll end up getting is 1 megahertz, and let's say we make this let's just say 28 megahertz. So then at the output, like Vaibhav kind of showed earlier, we'll get the sum and difference frequencies of this. So we'll end up with 29 megahertz and 27 megahertz on the output. Then you can stick a filter on that to extract out whichever one of those two you're interested in. Okay.
Yeah, okay, that makes sense. So your input is always the IF, not
No. So that's for the transmitter, but keep in mind when you're receiving, right, your microcontroller has a DAC for 1 megahertz, but it also has an ADC of 1 megahertz. So you can't directly take a 27 megahertz signal from the antenna and plug that into your microcontroller because the sample rate would just be abysmal. Like it's only updating 1 in every 27 actual phase switches that you might be getting over there, right? Not exactly, but yeah. So this general principle applies though, where what this does is it mixes so the way this works then is if you input your 27 megahertz thing here, and then you have this be 28 megahertz, at the output here you would get 1 megahertz and
55 megahertz.
yes, there you go. So that's where you would have your input at RF.
Okay. Well, I mean, okay, so that makes sense. So another thing is, you seem to show that IF either equals RF or minus RF, right?
Sure.
So how does the mixer, like, where does the mixer capability come in?
Okay, so good question. So this is only for a moment in time while IF or while LO is +1 or -1. So this keeps switching between equals RF equals negative RF. So I think the easiest way to see this is I'm going to. Are you guys good with this? I'm just gonna erase. Stop this for now. I guess no one answered, and I just started erasing. So you better be good with it. Okay. Okay. I'll just do the whole thing for now. Okay. Okay. So I said earlier how LO is more or less a square wave with going between +1 and -1, right? The Colpitts oscillator output will be a little distorted, blah, blah, blah. It looks like a square wave. So what do we know about the frequency spectrum of a square wave?
Frequency.
Okay, so it's going to have the fundamental. So let's say we built a, 22 megahertz oscillator, and it output roughly a square wave. So I'll have some frequency here. Then we're also going to see odd harmonics, right?
Mm-hmm.
So we'll see, I think 66. That's 3. What's 5 times? That's 110. Yep. So we'll just keep seeing them, and their amplitudes will roughly decay, kind of like a sync function does. Okay. So and then we want to. So if in the time domain, what we've done is we multiplied our RF signal by +or -1 back and forth, right? We've multiplied it by a square wave. Okay, so even though in the time domain it's just alternating between equals RF and equals -RF, some interesting things happen in the frequency domain. So let's say we have just 1 megahertz here. So what we're going to get when we do this, it's going to be what's that fun symbol we like? Okay, so what we're going to see is around let's see. We're going to see a bunch of these kind of happen. So essentially, instead of just multiplying 2 sinusoids together, where you just get sum and difference frequencies, we do that except with every harmonic. Okay, and then next lecture we'll talk about, we have all these harmonics at the output with this type of mixer. So we're going to design a filter to get rid of the harmonic content we don't care about. Yeah. So that's a really good question, and it's kind of weird to see like, you're multiplying by a square wave, and it's either equal to it or equal to its inverse. How do we get this? But just because of the transitions every other period, whatever, the result in the frequency domain is you end up with sum and different frequencies at every harmonic. Yeah.
So it helps to think about it as well, right? Like at the RF, so let's say you input this at the LO, and at the intermediate you have something like this or whatever, right? At the RF, you won't exactly get this or whatever the multiplication is supposed to be. At the RF, because of that switching feature, you'll likely get something that's a bit more like this. And you'll get this really messy, like it'll have a whole bunch of different jumps up and down and something like that. And when you simulate it and you start looking at the mixer outputs for the first time, you see this. It's basically like a whole bunch of different things happening, which is all of this happening. It's when you pass this into a filter that you then get this. So the way you get the clean cosine you want for transmission is through the filter. The mixer just kind of gives you the base, at least what you want to work with, so that you can then start filtering out the rest. Because earlier we didn't even have what we wanted. So this just gives you what you wanted along with some other crap we don't want, and then we filter that out. So the plus minus RF action doesn't immediately intuitively give you this. It gives you this messy like jungle of almost like a square wave, like a sine wave that's more like a step ladder function. It'll become a bit clearer when you see it in simulation, but that's kind of what it looks like a sine wave that's chopped up into a whole bunch of bits. But when you like filter that is when it becomes a bit more clear that okay, this is what I want.
Yeah. In the time domain, it'll look kind of like this. You'll have RF, and then you multiply it by plus minus 1. It'll keep jumping like this. So you get all these like packets like this. But then the result ends up in the frequency domain. Take FFT of this, you'll see that the sum and difference frequencies are present in your output waveform. Okay, I think that's most of it. Brief note about LO and IF and RF isolation, right? Okay, I think okay. All right, tell another joke by Bob while I draw the rest of my circuit.
I mean, I don't really have any more jokes. I suppose I can take any other questions you have about why this works. All right. I guess I can. I'm not going to try to make another joke. The first one didn't quite get the warm response I thought it would. See that he laughs at. You see my point?
Okay, I think that's it. Okay, I'm just going to briefly touch on, and we'll mention this a lot more in the assignment because you'll actually be measuring it. But there's a few different mixer properties that are of interest. So, like Bob said, an ideal mixer just simply multiplies two signals together. But in the physical manifestation of them, they're not perfect. And so when you multiply two signals, you should just get the sum frequency and just get the difference frequencies, right? But there's something called leakage, so you might actually see some of the, so instead of just seeing sum and difference frequencies here, you might see some of the, you might see the LO frequency, which is right in the middle. You might see that present, or you might see the RF signal. You might see some energy from those frequencies present in your output waveform, which is undesirable because it makes it so your filter has to be a little narrower, I believe. Yeah. So let's see. So the desired behavior is for there to be what's called LO isolation, where that whatever frequency content is there is not present here at the output. So I'm just going to call this IF again. Okay, and then there's something called RF isolation, where the exact frequency content present here isn't going to be directly at the output. And there's two different categories of mixers. One's called single balance, and a single balance mixer will have either RF or LO isolation, but not both. Whereas a double balance mixer will have both LO and RF isolation. And let's see. So the diode ring mixer happens to be double balanced, which means it has both. So you can kind of see that by no matter, you remember how earlier I kind of simplified what the circuit ends up being over here, and it simply becomes just two transformers, or one transformer like this, and then RF, and then IF. And that's because regardless of what's happening here, the voltage here is going to be 0 volts, or the voltage here is going to be 0 volts. Like, it's going to be stable. And then LO doesn't manifest anywhere here directly in the output. So let's see. Yeah. So
isolation.
Yeah, hence isolation. If the windings aren't perfectly symmetrical, so like maybe this one has slightly more, like 0.1 turns more than the other, or maybe the diodes aren't, well, in real life, your diodes will never be exactly equal. If they're close enough, then this will be roughly 0, approximately 0. But let's say the saturation current for one of them is just slightly more, then it won't be perfectly symmetric. This won't be exactly 0. It'll start being impacted by LO, and then you'll see a little bit of leakage into the output frequency spectrum. Let's see. As far as RF, let's see. It's a little weird to see because I wrote earlier how the output is equal to either positive RF or minus RF. But kind of take the intuition we had over there, where let's say RF looks like that. Then up here might look like that. Down here might be the other way around. So kind of sums up to 0 in the middle. Let's see. Okay. Let's see. I'll put a note in the assignment, and also we'll write out a notes thing better. We'll release some handwritten notes along with the lecture afterwards when we release the assignment to talk more about where the RF and LO isolation comes from in the mixer, because it's a little harder to draw out. But we'll leave it that for now. Okay. By above, what else do we want to do?
I suppose one last thing that might be useful for the assignment and that we can discuss now is, okay, so actually before we do that, is there any more questions about the mixing part of this?
Yeah. Okay. So I'm just trying to picture. So if you have like, let's say a 27 megahertz at the LO, or let's say you have 1 megahertz at the LO.
Okay.
And you have, let's say you're injecting at 27 megahertz, where your mixer should give you 26 and 28, right? So where do you see the 26 and the 28 in this diagram? Like at what point? At the RF?
But it depends on where are you injecting your 27 from.
Let's say you injected at IF.
Then you would see 26 and 28 in RF along with okay, so for one, I'm actually not quite sure how this works if LO is a lower frequency than IF. That's something I would actually be interested in trying to do myself in MT-Spice. I haven't done. I'm not sure if this works.
Hey, okay, that's fine. Like, well, let's say we meet this specification.
Okay.
Of what LO needs to be with respect to IF and RF. Let's say we meet that.
Yes.
So then, how do you see 2 different carrier waves at RF? And if you see 2, are they like summed up into? Are they summed or?
They're superimposed over, or they're superimposed on one another.
So how do you differentiate the 2? You filter.
Yes.
Oh, so you're gonna okay. So if you say what you're gonna get at RF is a combination of a 26 megahertz wave plus a 28.
Yep. Plus a 27 into 3 minus 1, 27 into 3 plus 1 plus the 5th harmonic plus
whatever
other stuff. Yes.
Yeah. So then you have to filter everything else out.
Yep. So you just define a bandpass filter around whatever carrier you're interested in.
And then you just filter that out. Okay, that makes sense.
We'll touch on that more
In our fourth lecture on RF
we'll just
filters.
touch on it, like that'll be the subject of the lecture, how to filter.
Yeah, building RF filters.
Yeah.
Okay, so then just one more follow-up question in terms of circuit.
Yeah.
Where does the summing happen? To get at RF, to get the 26 plus 28, where does the summation happen? So like I get it, like your LO, once it goes to the transformer, one is at 27, one is at minus 27. It goes through 2 of the 4 diodes. And then what happens when it hits the other transformer? I think I missed that part. Can you bring that again?
What do you mean by when it hits the other transformer?
So like, let's say a 27 megahertz wave goes through the top end of that transformer, right?
Okay, so
Yeah.
27 in here.
Yeah, you put 27 in here. When one of them gets flipped, one of them is 27, so you get 2.
So okay, to to kind of help make this clear, you're not taking LO and in any way like directly multiplying it to RF in this circuit, right? What you're doing with LO is basically operating a switch really fast to more frequently flip RF or IF in this case, right? So IF is oscillating at some frequency, and you're basically flipping, you're using LO to drive a switch that's flipping between IF and negative IF much quicker than IF itself might be making that switch, and then seeing that output at RF. So it's not so much that you're seeing the 27 megahertz from this travel through this circuit into these transformers. It's more that you're using the 27 megahertz to use this as a switch to choose which transformer you're actually seeing at RF.
Oh, okay.
And that's where your harmonics come from as well, where that's more a function of the harmonics coming out of the imperfections in that switching process. It's not so much that you're taking this frequency physically into here and adding that sine wave into this sine wave. Like physically, you're just using that sine wave to kind of drive this
you're
switch.
just flipping, so if you had 27, you're just flipping in between 1 and -1, which is the IF, and accordingly, like, you'll get a sum, 27
Yes.
plus 1, 27 minus 1, and then based on which transformer is active of the two right transformers,
Yes.
you'll see the 26, 28, and then like a sum of both of them.
Yeah, it kind of starts, yes.
It kind of starts mixing into each other.
Yeah.
That's how you get a 26 plus
Yeah.
28, and then you filter it out.
Yeah.
Okay.
Okay. Got any other questions for us thus far? Okay. All right. That's
Alright, so that's everything to do with mixers. What's the time right now?
655.
6:55. Alright, really quick, I'll just start the conversation on this then. And this is something that will be discussed more in the assignment again, but one thing to think about, so forgetting everything else that this does with all the mixer stuff and just forgetting all of that, right? At its core, this is an inductor coupled with other inductors, coupled with a whole bunch of stuff over there, and there's a whole bunch of frequency stuff happening, right? So what would you do if I asked you to find the input impedance?
Try.
Yes, exactly. Like it's a lost cause. Like you can, well, I'm sure someone's bothered to do the theory behind it.
Yeah, I
and
saw the video.
done fancy stuff. If you can look that up on the net later, but there's no point in worrying about it, right? Like you look in here and it's like, well, what the fuck is this? So you have your LO at 4 megahertz, and your output from your LO, if you remember, comes out from your emitter, right? And you have a resistor there that you've chosen very carefully to get the right GM to actually get the amplitude you need. If you just plug that into this, you then have that resistance in parallel with something that you kind of have no control over, and that is likely time variant as well, depending on what's happening here. And so your carefully designed bias point gets fucked, right? And so now your LO, you're not always sure if it'll work the way you want it to work. You know, then you basically have to worry unnecessarily about what values you're choosing for these inductors, and a whole bunch of other stuff that's just really not worth getting into. So if I have a block here and another block here, and I want to insert a buffer that does nothing but provide good impedance on the input side while protecting me from stuff on the output side, what would this block be based on what we've discussed in the first two lectures?
Common collector.
Yes, this would be a common collecting amplifier. And what would you want the gain to be?
About 1.
About 1, exactly. You would want this to be as close to 1 as possible. So in assignment 2 for intellectual exercise, we tried getting it to 0.5. But this is actually a much more common use of common collector amplifiers. Anytime you have weird, unpredictable behavior on your output side, like you use this because you can much more carefully control Z in by choosing your bias resistors, and by choosing, you know, other things. We discussed that formula. It's R1 in parallel with R2 in parallel with R pi going in beta plus 1. There's stuff happening there, right? So that's something that we can design around much better. So that's something that you see in the assignment, which is you have your oscillator going into a common collector of gain 1, going into your mixer. Yeah, so that's everything for today. And you know, we have a good break tomorrow, and yeah, we'll see you guys on Saturday.
Save the line by Bob.
See you then.
That's a wrap.
Oh.
All right.
That's a wrap.
All right.